कल तो डिस्कशन हो गई एग्जाम
So I'll try to work with the embedding. So let's see if we can actually enumerate something on the pattern mining side, because we never did anything on the pattern side. So let's see how we can take iGraph and write our own small code to extract the embedding, because we've been talking so much about pattern and embedding. So let's see what we can do with that. Everything from scratch. We'll not use. We'll just use the iGraphs just for the adjacency matrix and things like that to query. But everything else will code on our own. So first we need to make a graph. So let's make a graph first. Okay, so let's make one graph up. So let's say there's a node here. There's a node here. So I'm going to use this network. Maybe we can add this. Okay, so vertex number 1, vertex number 2, number 3, number 4, number 5, number 6. And let's give them some labels so we can find something with the labels. So let's say this is A, B, D, A, B. Okay, this is the graph that I want to create. So what we can do is we can take the topology of this graph and we can make our standard graph like we've been doing so far. And then the labels, I'll keep them in a label vector, so separately, so that I can refer to them. So this graph is basically, let's make the graph. Anyway, so this is okay, so G is graph, edges, directed, equal to false, edges equal to C. So what do we have? 1, 2, 1, 3. 2, 3. Okay, then we have 3, 4, 3, 5.
4, 5, 4, 6.
3, 4, 3, 5, 4, 5, 4, 6. And then 5, 6, right? Plot G. Alright, this is an answer. Okay, but we do need the labels, so I'm going to put the labels in a vector. Let's call that the vector L. It's C of, and now we just give the labels that we have. So it's B, D, A, D, B, A. D, B, A, D, B, A. Okay, so these are just string labels, right? Or character labels. Okay, so now we have the labels and we have the edges. So this way I can of course query the, let's say the label for the first vertex is B. I can find the labels. And then I need the adjacency matrix. So A is the adjacency G star equals to false. So that gives me the adjacency matrix for the graph. Okay, so let's start with a simpler problem first. I want to find all the cliques in the graph. Okay, all the cliques. So cliques are complete subgraphs. And so the first level cliques are easy. Okay, the first level cliques are all the entries in my adjacency matrix, all the edges basically, right? And for the cliques, we're going to ignore the labels. So right now, I'm not going to use the label information. So it's purely a structural, what comes out of this. And so what we hope to see is that there are going to be these three triangles, right? The 1, 2, 3, 3, 4, 5, 4, 5, 6. Those will be the three cliques which are triangles. There's no other clique in this network. I mean higher clique. So the clique part would be, let's think in terms of the embedding, right? So in terms of the embedding, we need to basically list out all the embeddings. So I'm going to basically make a list called E, and have to see. I think this will, the list. Oh yeah, I can say list. So E is going to be a list. Right now it's empty. I'm going to add all the embeddings in this list. So what we just do is for I goes from 1 through, I in 1 through 6. Then for j in I plus 1 to 6. Actually, I want this to go back up. Okay, let me just kill this. I'm going to do a new one. Okay, so for I in 1 to 5. So because it's an undirected network, we just only have to go up to vertex 5. And then the second loop will go from I plus 1 to 6. So that way I'll get all pairwise information. Or should I do everything else? Let me think. 1, 2, 2, 1. Yeah, that's okay. Okay, so this is a new loop. Okay, so what I'm doing is I just made E equal to an empty list. Okay, and now I'm going to write my loop. So for I in 1 through 5, for j in I plus 1 through 6. So I just want to go over every edge only once for now. That should be enough to get me all the distinct. Because I just want to know the distinct, because the labels are not important. So I just want to know the distinct edges in my network. And so all we're going to do is we're going to say is that E is equal to now I have to check what the I think it's function. Is it append? Append C I if so I have to say if Aij is equal to 1, right? So only for those edges that are present, we want to do something. So I'm doing this like in an extremely naive manner, right? So I'm just sort of laying out all the logic. So what we want to do is that for every edge that is 1, add to E. I have to check whether this actually works. I probably should have used Python for this. Append C of ij. Now C of ij will take that pair and it will put that edge in my list if this thing works. So I have to, I keep on forgetting what the syntax is. I go from Python, it would be easy. Now in R I have to do it this way, and it may not work. Let's see. And that's it. Yeah, there's no append. So let me check what the append function is. So if I have append E C12.
Square bracket.
That has made it, so okay, so this made a list, but the problem is that this list has 1 in one place and 2 in the other place. I want the pair 1, 2 to be together. So the pair 1, 2 together is, that's a good question. Supposing I did this first. Nope. Okay, so now so what you have to do is you have to give the index of, so this double bracket actually is a list extension function. So I'm going to be using that to add a new tuple to the, so I mean, these are the syntax of a language, so it's a little bit more tedious to do this in R. In this case, actually, Python would have been faster. But anyway, let's redo the whole thing with the new thing that we know. So first we initialize the list to empty. We basically make the first for loop. So I want to go over all the entries of the matrix. Then I want to go over all the j entries of the matrix. Then I want to check whether that edge exists. And then if the edge exists, what I want to do is, and again I made a mistake because I should have put a counter. Okay, I don't have a counter here. So this is all going to be several iterations. Finish it off. Okay, so E, so fresh start again. E is list. I need an index, okay? This is the list index. So I'm just going to call it index I is initially 1. So every time I add something, I'm going to increment the index. Okay, now I'm ready to do the for loop. So I can just copy paste. Paste. Copy paste. And then copy paste. Okay, so what we want to do is we want to say E of index, because that's just the double bracket basically says insert at that index a particular item, and the item I want to insert is ij, right? So that edge exists, so I put that in, and that's it. So then I close it off, then I close it off, then I close it off. So this should have given me now all the edges in my network. So let's see. Oh, I didn't increment the ID. See? So you guys know better than me. Alright, redo. Should have caught that before I finished the loop. Okay, now I increment IDX. Now we close.
Condition.
Sorry?
If we are
But no, but this is giving me. Yeah, that's much better. Actually, yeah, why am I doing the hard way? Now that makes sense. Okay, so let's do. I'm going to use Vim. I don't know how many of you know Vim. It's a very interesting package. Okay, so what I want is, yeah, so let's do it much easier. So I'm just going to type the thing here. So first we make E, no, I have to do the whole thing. Oh, no, we have the graph already. Okay, so let's say E is equal to list, IDX equal to 1, and then I can say for I in 1 to 5, for J in 1 I plus 1 to 6. If Aij equal to 1, now we do E of IDX equal to Cij, and then we say IDX equal to IDX plus 1, and then we close, then we close, then we close. Okay, so now we have this, let's run this. Alright. So, E is now a list of all the edges. So we can see that we have, see what happens to this. Okay, so as you can see from this one, so now we have all that is 1, 2, 1, 3, 2, 3, 3, 4, 3, 5, 4, 5, 4, 6, 5, 6. Okay. So what do we have to do next? So what we have to do next is, for every embedding now, right? Since now we have all the embeddings, I need to add one more vertex and then check whether or not I still have a tree. So I'm going to go back to this and do the logic here, and then I'm going to copy and paste here. So get rid of this. We don't need it. Okay. So now that you have the list E, we have to say for all edges in E. Okay, so for actually that's good. So how do I know? Okay, yeah. For I dx for I in 1 through the length of E. Let's see. Okay, the length is good. So we're going to use the length to fix the spelling, of course. Okay, so I'm going to go through each edge, right? Or rather each embedding. So let me call it, yeah, this is the index. So for I in 1 through length of E. So first, let's say, we say this is an embedding. Embedding is E of I, right? So I'm just going to copy that embedding into E. And now I know what that E looks like. So I have to look for the neighbors of E. So E has two things, right? So if I say E of 1, let's say if I say E is equal to the first edge, so then if I print E I get 1, 2, and I can say E of 1 will be the first vertex and E of 2 will be the second vertex. So from each one of these I'm going to now do the extension. So I need to know who the neighbors of 1 are, who the neighbors of 2 are. So that we can get from the adjacency matrix. So coming back here, what I can say is that for E0, so and I'm doing this like the naive way. I mean, I could have actually used the R function, but let's just do it the blind way. So I'll say for J in 1 through 6, which is the number of vertices in my network, I want to find the neighbors of E0. Okay, so basically this is find the neighbors of E0. So V0. So these are all, or the N0 is the neighbors of, so this is again going to be a list. Okay, and I'm going to repeat this for the second vertex. So for this one I'll say all the neighbors of the first vertex in E. So for neighbors of E0. So I'll say if A of E0 comma J equal to 1, right? So E of 0, sorry, no, not 0, E of 1. I mean, in R, everything begins at 1. There is no 0 index. There is again a difference between Python. Python, you have a 0, R, you have a 1. So all indices in R are from 1. So I'm saying from the first vertex, and actually let's just make it 1 then, so that we are consistent. So from the first vertex, let's look at all the neighbors and put it in this list called N1. And again, since I'm doing the hard way, because I'm sure there's an easier way. I mean, I'm sure there is an append command which I can't think of right now. So this index is 1, and so I'm just going to now basically add N1 IDX equal to J, and IDX equal to IDX plus. Okay, and then we just repeat the whole thing again for the second vertex. Copy. And paste.
So can you please increase the font of this?
Oh, diagram? Okay. Good point. Edit font. Okay, so I basically copied the whole thing again. I'm just going to call this N2. Index becomes, that's fine, this becomes E2, this becomes N2. And so now I have basically all the potential extensions of the edges. I know now from the first vertex who the neighbors are, from the second vertex who the neighbors are. So N1 and N2 now contain most of the information I need. Okay. So let's just first, before I do anything else, just let's just run this and see it did the right thing, and then I can come back to this code and then finish it off. So close the loop and we should be good to go. So let's, if I run just this loop, what do I get? Oh, I do need to, I should probably print them out. So let's print them out. So I can say print N1 and I can print N2. So I'm just saying, what for every edge, and of course let's also print the edge, E. So this way I'll know whose neighbors I'm printing out. And let's run this code. Copy. And paste. Okay, so let's see if this gives me the right thing. Yeah, so for example 5, 6. So this is the this is the E, and it says that for the first vertex you have 3, 4, 6, and for the second it's 4 and 5. So let's see. For 5, it is 3, 4, and 6, and for the 6 it is 4 and 5. Right? So I mean I didn't print out the header here, but the list index tells you, right? So 1, 2, and 3 is the first N1. 1 and 2 has to be the next N2. So 3, 4, and 6 are neighbors of 5, and 4 and 5 are the neighbors of 6. So that did the right thing. And so now what I have to do is I have to do now in this code I have to actually try whether or not it's going to be a triangle. So I now know the neighbors, but for every neighbor I'm going to basically modify this code so that I can test for the neighborhood. So here's what I'm going to do. Before adding j, right? So I don't want to add j to my thing. J should only be added if j connects to both the endpoints. Right? You see the point? Because I have to do a clique, I have to do a triangle. So the j should not be added as a neighbor unless j connects to both E1 and E2. So that's what you have to check here. So I have to say if A of E1 j equal to 1 and A of E2 j equal to 1, then this thing should be. Right? Makes sense? Because, right, I'm looking for an extension. Like, for example, go back to this example. So I'm saying, should this 3 be here or not? Right? So I'm starting from 5. I'm saying 3 is a neighbor of 5. And I want to add 3 as a possible media click. But if you extend from 5 to 3, 3 should also connect to 6 to make a triangle. Otherwise, it doesn't make sense. So only those vertices will be added that actually make up a triangle for the next step. So that's pretty much this logic that I did here. So I added this one extra check, and then I can just do the same thing for the other one.
That's the first one. You can remove the first step.
Well, I guess, yeah, if it's an and, you can get rid of it. Yeah, it's redundant. Okay, so now we simplify this. Makes sense? Get rid of this guy. I actually don't need that. Okay, so now we have, I think now we have it. So we can just replicate this here. So if 2j is 1 and actually then I don't need this. Yeah, then I don't need it. Alright, cool. So then let's get rid of it. So we can simply remove this whole thing. Okay, so now I want to make a new list. So I'm going to call this the list E2. IDX2 is 1. And what I'm doing in this is actually, instead of saying N1, I don't need the N1, I just want to make a new extension. So I'm just going to add it to this E2. So E2 of index 2 is going to be C of E0, sorry, E1, E2, and J. So I'm now keeping a triple, right? So the point is that from an edge, go to a triple. So the triple is basically made up of this triangle, right? So we just verified that if you pick the E edge, the two endpoints of that, E1 and E2, are connected to J. So I'm just pretty much writing that out as make a new list called E2, which has all the endpoints E1, E2, and the new vertex J that's connected to both of them, and then increment this index by 1. And keep on doing this, and then simply print out E2.
So in length also it will be
No,
E2?
no, no. This length is correct. I mean, we are going over the previous embedding, right? The previous embeddings are of length 2. So it's the length of all the single edges. And now for every one of those, I'm finding out who the neighbors are. So this length is correct. This is, I think it should work out. Okay, so I think that should work. Let's see. And so we have it working, except that it has duplicates. So we knew that they were going to be duplicates, but you see the embedding. So this has actually listed out all the automorphisms also, right? Because I'm extending from every endpoint, right? From every initial starting point. So we have 1, 2, 3, 1, 3, 2, 2, 3, 1. Those are all the automorphisms of this triangle. 1, 2, 3, 1, 3, 2, and 2, 3, 1. Same thing, 3, 4, 5, 5, 4, 3, 3, 4, 5, 3, 5, 4, and 3, 4, 4, 5, 3. Then you have the 4, 5, 6. So this is what you have to do now, is you have to eliminate duplicates. So if it's the same clique, because here the label is not important, so actually one would, but at least we got some of the automorphism of the thing. So what you have to do now is you have to write the code to get rid of duplicates. In the case of cliques, actually it's very easy to detect duplicates because you have 3 numbers, and in this case the labels are unimportant. So, and they're completely connected to each other. So actually I can define the canonical form very easily. The canonical form is actually going to be in increasing order. I can just say that for every representative, all your numbering should go increasing. That is the only canonical form. Because they all automorphic to each other, they're completely connected. So in this case it would be easy to say that the only canonical representatives are the 1, 2, 3 is the canonical member. Okay? Because the 1, 3, 2, the 2, 3, 1, they are not canonical. I can find a simple permutation of the numbering because everything is connected. Topologically, there's no difference between 1, 2, and 3. So the vertex number 1, let it come before 2, let it come before 3. So that's going to be canonical. 3, 4, 5 is going to be canonical, and likewise 4, 5, 6 is going to be canonical. So in this case, it's actually for cliques, eliminating duplicates is very easy. Simply sort the IDs and you get it. So here you could actually write the logic if you want, which would be that now I can do the following. I can say that for I in 1 through the length of E2. Okay, now I'm going through all the extensions I found and I want to eliminate the non-canonical ones. So what I want to do in here is I want to basically say that for j in 1 through length of E2 of I, if E2 I j is greater than E2 I j plus 1, found equal to false, or rather canonical. So I'll assume that everything is canonical to begin with. Okay. So the idea here is that for every tuple, I want to make sure the tuple is sorted in increasing order, right? So I could have just sorted them and done it that way, but I'm doing everything in the simplest way I can think of, which is let's just compare the jth element with the next element, j plus 1. Okay, if j plus 1, if j is greater than j plus 1, you have a problem, right? It should only be strictly increasing. You should not have a decreasing solution. So if this happens, then canonical becomes false. And so now we just say that if canonical, actually I can just say if canonical, then print to j. Okay, does that make sense? So essentially what we're doing is we're saying that I'm going through all the extensions I found, okay, which are in this list E2. I'm going to basically check, set a flag called canonical, which is true or false. Initially everything is assumed to be canonical. And then I look at that embedding, that tuple. And all I'm checking is that there should never be this case where the j is greater than anything that comes later. It should always be less than that. If this violation happens, we say canonical is false. And then we only print out those embeddings which are canonical. And actually we don't need the length, it should be length minus 1. Because we don't want to test the last one. It will be an out of bound index. So this is the final code. Basically, I go from 1 through length of the tuple minus 1 and test this. So I think that should do it. If I didn't make any mistakes, then this should work. So copy and paste. So there is a problem somewhere. If canonical, there's a syntax error, I guess. So let's see what it is. Unexpected symbol.
Print equal braces.
Yeah. Oh, I know what I mean. Okay. This one is not E2 minus 1, it should be length of E2 minus 1. first you compute the length of the vector and then subtract one from it. Okay. Okay, final attempt. Hopefully it will work. Nope. What happened now? Comparison of these types is not implemented. Okay, 3, 2, 1, 1. I think I know the problem. It's supposed to be this. So it's that list element. So this is how we debug. So it's actually not E2 of, because it's the list element, so it has to be a double bracket, okay? So the list index goes by double bracket. Now, hopefully, it will work. Okay, let's try this again.
वो लिस्ट के लिए ना, ये मैट्रिक्स में है ना, ये मैट्रिक्स में वो लिस्ट है, लिस्ट को ऐसे एक्सेस करते हैं।
Aha. Alright, let's put this code up here. So this is what we did, right? So essentially, I just wanted to, as I said, there's probably easier way to do this, but I on purpose went through the whole exercise of doing it the most naive way I can think of doing it. And so essentially, yeah, that's what we did. So basically, now you can repeat. So actually, I should have put this in a subroutine. And now this would become then generic. Basically, for every vertex, you extend. Every time you extend, you basically check whether you're connected to everyone before that came, before. And then you enumerate all these things, put them in a list, and then simply eliminate the non-duplicate ones. The non-canonical ones. And so only the canonical ones will get created for the next step, and you continue. In this small example, there will be nothing else to find. So we will not do this because there is no other extension you can find. For 1, 2, 3, right, there is no fold size key. So this is an example of how the embedding, so at least it gives you an idea of, when you talk about embedding and patterns, how we actually, list them out. So one more thing you want to do is for labels, because I've not yet looked at labels. So let's just add that component and then we'll be done. So for labels, I'm not going to do the full thing, but let's just say we want to count how many ABCs you have. How many AB, what was my data? Let me draw it here. So then that will pretty much wrap up the whole topic. Okay, distributed graph mining. Alright, let's just, okay, we can figure out from here. So we know the labels, right? So let's just print out the label, L. Okay, so this one was BBA. Okay, so I want to know the patterns ABB. Okay, how many ABBs do I have? And 4, 5 is also B. Okay, so there will be 2 instances of A, B, and B. So the pattern is, pattern I want to count is A, B, B. Okay, A connected to the B, A connected to the B. So this would be so I want to know for every embedding, okay, for every embedding, what the labels are. Okay, so let's first make a pattern graph. Okay, so I need to make a pattern graph P. So P is a graph, and this graph is basically directed equal to false, edges is equal equal to C, and I'm going to assume that I have basically three vertices, 0, 1, and 2. Okay, 0, 1, and 2. I'm sorry, the edge between 0 and 1, 0 and 2, or let's just say 1 and 2, and it doesn't really. Or 0, maybe. Okay, let's just start with 1. I'm not sure how R will react to 0. 1 and 3, and then 2 and 3. Okay? So this would be like a generic pattern. So these IDs are different from the other IDs that I have. So this is just the IDs that are internal to the pattern graph. Okay? And then, so if I plot G, plot P, you're just going to get a triangle. But now I have to add the actual canonical pattern. The canonical pattern would be A connected to two B's. So the vertex label 1 should be the A, 2 and 3 can be B's. So the label for P, so I'm going to call it LP, is simply going to be C of A, B, and B. Okay, so this is my pattern. So I basically can look up what the connectivities are. So since I know E2, right? So I'm going to skip a lot of steps. I'm just going to show, right, that from these triangles, since I know now all the triangles, I can just check which of these triangles matches my pattern, right? So it's basically like it's an isomorphism between every tuple in E2 versus P. So I just have to make sure I can find such an embedding. So what should we do? So we have the, so this would be a third code. So now I'm going to do basically how to match E2 and P. So let's see what I can do here. So this one should be basically try all possible permutations of E2 and then see if you can find a match. Okay, you know what the easier way would have been? So I'm going to replicate this and I'm going to get rid of the canonical equation and I'm going to do it because, I mean, in a code you do it a different way, but this is actually easy for me to simply enumerate everything and don't worry about the canonicality yet. Just check the topology first, right? Because I have all the triples in all possible permutations. So why don't I just check the topology of those guys, and that should give me the right thing. So get rid of this code here. So what I want to do is I want to say I could have just written 2 lines. Okay, so what I could have said is that for every triple that I already have in my set, for every triple, just check whether the topology is met or not, right? So basically I have 3 vertices in E2 and I have 3 vertices in P. So I have to say basically if the label of if the LP of 1 is equal to the label of E2. Okay, first let's make our life a little bit simpler and compute the match. So I'm going to call this let's just call it E is E2 of I. Okay, so I'm extracting the triple and then I'm just going to check the labels first. So the labels should match. So LP of 1 should be equal to L of P of 1, right? And then we just replicate this 3 times. LP2, LP3, E2, E3 should match. Okay, so that definitely should match. And then if all the labels are matching, then the edges should be there. So now I have to check for the edges. I have to say that if I mean, like I said, this is a tedious way of doing it, but let's just do it. This would be A of this is getting hard. E of 1 E of 2 equal to 1, and I'm actually assuming there are no P. Okay, so otherwise you have to actually do much more. So you can see that this thing gets really complex very fast, even for a small graph like this. Here I'm assuming I know the structure of P and I'm just using that. Otherwise you actually have to check in both the pattern and the derivatives, and then only you're able to find. But let's just finish this off. So we'll just say paste. Oops. Okay. This would be 1, 3. Should be 1. And then finally 2, 3 should be 1. Okay, in this case we can print out the embedding. So now I'll say in this case print out print it. So hopefully this will get me the mapping for A, B, B. Okay, let's see what we can get out of this. Copy, paste. What happened? Okay. That doesn't make sense. Oh, which one you mean? Why did I find these are isomorphic to each other, that's correct. So it found only one of them. Okay? It found only one of them, which is interesting. It found only the 3, 4, 5 and the 3, 5, 4. Yes, okay, I know why I didn't find the 1, 2, 3. So if you look at this, this is a B, this is a B, the 3 is an A, right? So for it to find the right one, the 3, 2, 1 should have been part of my embedding list. So let's see what my embedding list looks like. So list, E2, and this is exactly why this hand-coded thing did not work, is because when you look at the, actually one second, go back here, because I made some assumptions, right? I made that I didn't actually try all possible rotations of the pattern. These embeddings, right? The first one is 1, 2, 3. Okay. Now 1, 2, 3 does not correspond to A, B, B because the vertex number 1 does not match the A. Likewise, this will also not match the A, and this 2 will also not match the A. It's actually the third vertex. So but there is a permutation. I mean, there is a way of rearranging this. If it had been 3, 1, 2 or 3, 2, 1, okay, I would have actually found the 3 had to come first because of the way I wrote the code. So of course my code is flawed, but I'm just telling you that when you're finding matching of a pattern, right, it's actually you have to be worried about many different things. Okay, So you have to actually find the exact matching and then extend it. And of course, we had got lucky in the case of 3, 4, 5 that 3 happened to be the root, and that was an A, and the other 2 were a B, and we found them. But we also found 3, 5, 4, and that's because the B and the B can change. But that's fine. That's a valid embedding, because I don't know which B is which B. So we found 2 of them, but not 1. I mean 2 embeddings. So anyway, I guess that at least gives you an idea about what you have to do when you want to find the matches of a pattern, and there are a lot of subtle mistakes when you do graph pattern matching and discovery. So that's all I have to do. Thank you. So we'll post these slides, the ones that I covered today. They will be made available via email. So then I'll see you all tomorrow. All ready for the exam?
Silence.